morning, dear students. This is Dr. KSNV Prasad, Assistant Professor, Department of Chemical Engineering. In this class, we will be discussing about chemical process safety, and the topic is hazard analysis. Hazard analysis is one of the important factors that every student should remember. Process safety management. It is a management system that is focused on prevention of, preparedness for, mitigation of, response to, and restoration from catastrophic releases of chemicals or energy from a process associated with a facility. There are 14 elements of process safety management. Process hazard analysis, operating procedures and safety practices, hot work permit, emergency preparedness and response, mechanical integrity, pre-startup safety review, training management, management of change, incident investigation, contractors, compliance audits, employee involvement, trade secrets, process safety information. So these are the 14 elements of process safety management. Out of these, we are concentrating on process hazard analysis. Process hazard analysis. It is one of the most important elements of the process safety management program. A PHA or process hazard analysis is an organized and systematic effort to identify and analyze the significance of potential hazards associated with the processing or handling of highly hazardous chemicals. A PHA provides information that will assist the employers and employees in making decisions for improving safety and reducing the consequences of unwanted or unplanned releases of hazardous chemicals. Preliminary hazard analysis. A common method for establishing a crude risk picture with relatively modest effort covers selected parts of or the entire bow tie, that is, the initiating events, the cause and consequence analysis. Checklists used to verify status of a system using a written list of items or procedures. A checklist analysis uses a written list of items or procedures to verify the status of a system. Checklists may vary widely in level of detail depending on the process being analyzed. What-if analysis used to identify hazards, hazardous situations, or specific accident events that could produce an undesirable consequence. What-if analysis involves the examination of possible deviations from the design, construction, modification, or operating intent of a process. What-if or checklist used to identify hazards, consider types of accidents that can occur in a process or activity, evaluate in a quantitative manner the consequences of these accidents and determine whether safety levels against these potential accident scenarios appear adequate. Hazard. A systematic analysis of how deviation from the design specifications in a system can arise and an analysis of the risk potential of these deviations. Based on a set of guidewords, scenarios that may result in a hazard or an operational problem are identified. Basic concept involved in hazard studies is that processes work well when operating under design conditions. When deviations occur from design, operability problems and accidents can occur. Hazard. Hazard analysis is technique consisting on essentially 3 steps, namely estimating how often an incident will occur, estimating the consequences to employees, public and environment, plant and profits. Past experiences should be the basis and if such experience is not available, similar plant experience may be considered. FEMA, used to examine each potential effect failure mode of a process on the system. Failure mode is the symptom, condition or fashion in which hardware fails. A simple analysis method to reveal possible failures and to predict the failure effects on the system as a whole. Fault tree analysis, a systematic deductive failure analysis that focuses on a particular accident or undesired event called the top event and develops the underlying sequence of events leading to the top event. Cause and consequence analysis quantifies vulnerable zones for a conceived incident, and once the vulnerable zone is identified for an incident, measures can be proposed to eliminate damage to the plant and potential injury to personnel. SVA, a process in identifying and then preventing potential security weaknesses in a facility. LOPA, a semi-quantitative methodology used to ensure that process risk is successfully mitigated to an acceptable level. Checklist. The positive points are simplest of the hazard analysis, easy to use, contains yes or no type of questions, provides quick results, communicates information well, effective way to account for lessons learned. Negative points are not helpful in identifying new or unrecognized hazards, limited to expertise of its author. Some of the questions in checklist are: for materials, what process materials are unstable or spontaneously ignitable? What evaluation has been made of impact sensitivity? Has an evaluation of possible uncontrolled reaction or decomposition been made? What data are available on amount and rate of heat evaluation during the decomposition of any material in the process? What precautions are necessary for the flammable materials? What flammable dust hazards exist? What materials are highly toxic? What has been done to assure that materials of construction are compatible with the chemical process materials that are involved? What maintenance controls is necessary to assure replacement of proper materials? For example, to avoid excessive corrosion, to avoid producing hazardous compounds with reactants. What changes have occurred in composition of raw materials and what resulting changes are in progress? What is done to assure sufficient control of raw material identification and quality? What hazards can be created by failure of supply of one or more raw materials? What assurance is there of adequate raw material supply? What hazards can occur as a result of loss of gas for purging, blanketing or inerting? How certain is the gas supply? What precautions need to be considered relative to stability of all materials in storage? What fire extinguishing agents are compatible with process materials? What fire emergency equipment and procedures are being provided? For reactions, how are potentially hazardous reactions isolated? What process variables could or do approach limiting conditions for a hazard? What unwanted hazardous reactions can be developed through unlikely flow or process conditions or through contamination? What combustion mixtures can occur within equipment? What precautions are taken for processes operating near or inside the flammable limits? What are process margins of safety for all reactants and intermediates? What reaction rate data are available on the normal or abnormally possible reactions? How much heat must be removed for normal or abnormally possible exothermic reactions? How thoroughly is chemistry of the process known? What foreign materials can contaminate the process and create hazards? What provision is made for rapid disposal of reactants if required by plant emergency? What provisions are made for handling impending runaways and for short stopping an existing runaway? How fully is the chemistry of all desired and undesired reactions known? What hazardous reactions could develop as a result of mechanical equipment failure? What hazardous process conditions can result from gradual or sudden blockage in equipment? What raw materials or process materials can be adversely affected by extreme weather conditions? What process changes have been made since the previous process safety review? Similarly, for operations, when was the written operating procedure last reviewed and revised? How are new operating personnel trained on initial operation and experienced operating personnel kept up to date on plant operating procedures, especially for startup, shutdown, upsets and emergencies? What plant revisions have been made since the last process safety review? What special cleanup requirements are there before startup and how they are checked? What emergency valves and switches cannot be reached readily? What procedures are there to cope with these situations? What safety precautions are needed in loading liquids into or withdrawing them from tanks? Has the possibility of static electricity creation been adequately taken care of? What process hazards are introduced by routine maintenance procedures? What evaluation has been made of the hazards of screwed materials during normal and abnormal operation? How dependable are supplies of inerting gas and how easily can supplies to individual units be interrupted? What safety margins have been narrowed by revisions of design or construction in efforts to debottleneck operations, reduce cost, increase capacity or improve quality? What provisions does the operating manual have for coverage of startup, shutdown, upsets and emergencies? What economic evaluation has dictated whether a batch process or a continuous one is used? Similarly, for equipment, in view of process changes, since the last process safety review, how was adequate size of equipment assured? Are any venting system manifold? And if so, what hazards can result? What procedures is there for assuring adequate liquid level in liquid seals? What is the potential for external fire which may create hazardous internal process conditions? Is explosion suppression equipment needed to stop an explosion once started? What are flame arresters and detonation arresters needed? In confined areas, how is open fired equipment protected from spills? What safety control is maintained over storage areas? In the case of equipment made of glass or other fragile material, can a more durable material be used? If not, is the fragile material adequately protected to minimize breakage? What is the hazard resulting from breakage? Are slight glasses on reactors provided only where positively needed? On pressure or toxic reactors, are special sight glasses provided which have a capability to withstand high pressure? What emergency valves and switches cannot be reached readily? When was pertinent equipment, especially process vessels, last checked for pressure rating? What hazards are introduced by failure of agitators? What pluggings of lines can occur and what are the hazards? What provisions are needed for complete drainage of equipment for safety in maintenance? How was adequacy of ventilation determined? What provisions have been made for dissipation of static electricity to avoid sparking? What requirements are there for concrete bulkheads or barricades to isolate highly sensitive equipment and protect adjacent areas from disruption of operations. For piping valves, were piping systems analyzed for stresses and movement due to thermal expansion? Are piping systems adequately supported and guided? Are piping systems provided for anti-freezing protection, particularly cold water lines, instrument connections, and lines in dead-end service, such as piping at standby pumps? Are provisions made for flushing out all piping during the startup? Are cast iron valves avoided in strain piping? Are non-rising stem valves being avoided? Are double block and bleed valves used on emergency interconditions where possible cross-contaminations is undesirable? Are controllers and control valves readily accessible for maintenance? Are bypass valves readily reached for operation? Are they so arranged that opening of valves will not result in an unsafe condition? Are any mechanical spray steam de-superheaters used? Are all control valves reviewed for safe action in the event of power or instrument air failure? Are means provided for testing and maintaining primary element of alarm and interlock instrumentation without shutting down the process? What provisions for draining and trapping steam piping are provided? For pressure and vacuum relief, what provisions is there for flame arresters on discharge of relief valves or rupture discs on pressurized vessels? What provisions are there for removal, inspection and replacement of relief valves and rupture discs, and at what scheduling procedures? What need is there for emergency relief devices, breather vents, relief valves, rupture discs and liquid seals? What are the bases for sizing these? Where rupture discs are used to prevent explosion damage, how are they sized relative to vessel capacity and design? Where rupture discs have delivery lines to or from the discs? What has been done to assure adequate line size relative to desired relieving dynamics to prevent whipping of discharge end of the line? Are discharges from vents, relief valves, rupture discs and flares located to avoid hazard to equipment and personnel? What equipment operating under pressure are capable of having internal pressures developed by process malfunction is not protected by relief devices, and why not? Is discharge piping of relief valves independently supported? Make piping as short as possible and with minimal changes in direction. Are drain connections provided in discharge piping of relief valves where condensate could collect? Are relief valves provided on discharge side of the positive displacement pumps between the positive displacement compressor and block valves, between the back pressure turbine, exhaust flanges and block valves? Where rupture discs are in series with relief valves to prevent corrosion on valve or leakage of toxic material, install rupture disc next to the vessel and monitor section of the pipe between the discs and relief valve with pressure gauge and pressure bleed off line. Have any rupture discs been installed on discharge side of the relief valve? What provisions for keeping piping to relief valves and vacuum breakers at proper temperature to prevent accumulation of solids from interfering with actions of safety device are provided? Machinery, are adequate piping supports and flexibility provided to keep forces on machinery due to thermal expansion of piping within accessible limits? What is separation of critical and operating speeds? Are check valves adequate and fast acting to prevent reverse flow and reverse rotation of pumps, compressors and drivers? Are adequate service factors on speed changing gears in shock service provided? Are there full flow filters in lube oil systems serving aluminum bearings? Are there provisions for draining and trapping steam turbine inlet and exhaust lines? Are there separate visible flow drain lines from all steam turbine drain points? Are driven machines capable of withstanding tripping speed of turbine drain points? Are non-lubricated constructions or non-flammable synthetic lubricants used for air compressors with discharge pressures of greater than 518 kPa to guard against the explosion? What provisions are made for emergency lubrication of critical machinery during operation and during emergency shutdowns? Are provisions made for spare machines or critical spare parts for critical machines? Are there provisions for operation or safe shutdown during the power failures? Are vibration switches on alarm or on interlock for cooling tower fans provided? Preliminary hazard analysis. Preliminary hazard analysis identifies the hazards of a process and the hazardous situations they may produce. Possible causes, consequences, and recommendations for protective measures are addressed. A critically ranking may be assigned and used to prioritize protective measures. Typically, preliminary hazard analysis is used to evaluate and prioritize hazards early in the life of a process as a precursor to more detailed hazard analysis studies. Generally, it is applied during the conceptual design or at the R&D stage when there is little information available on design details or operating procedures. Commonly, it is used as a design to review tool before a P&ID is developed. It is useful in making site selection decisions and in analyzing large facilities when circumstances prevent other techniques from being used. The procedures for conducting preliminary hazard analysis is prepare and organize the studies, subdivide the process, identify the process hazards and hazardous situations, list the causes, specify consequences, assign critically ranking, identify any recommendations, document the results, resolve the recommendations, follow up on the recommendations. What if? WI studies involve posing questions relating to initiating events to identify hazard scenarios for a process. The PHA team brainstorms questions in a WI study. They can be used to study virtually any aspect of a process such as equipment, procedures, control systems, management practices, etc. Severity of injuries or illnesses. On the column side, we have likelihood of occurrence. If likelihood is frequent and severity is negligible, then it is medium. Similarly, if the likelihood of occurrence is improbable and the severity of injury is catastrophic, it is medium. So thus the rankings low, medium, high and serious are given and different values are also given. If the risk level is high, 12 or higher, operation is not permissible, immediate action is required. For example, if the likelihood of occurrence is frequent and the severity is critical and catastrophic, that is high, 15 and 20 points respectively, then the operation is not permissible. Similarly, if the risk level is serious, that is 7 to 11, remedial action is required on high priority basis. Like for likelihood of occurrence frequent and severity is marginal, like serious number score is 10. Similarly, medium 4 to 6, remedial action is recommended. For example, likelihood is remote and the severity is marginal or critical, medium, that is 4 or 6. Remedial action is recommended. Low 1 to 3, considered acceptable action, discretionary. For example, improbable and negligible, 1. Similarly, improbable and critical, that is low, 3 points. HAZAP. The HAZAP method focuses on investigating deviations from design intent such as no flow at a location in the process where flow is intended or high pressure in a vessel which should not exceed a pressure limit. By definition, deviations are potential problems. Example, no flow in a transfer line or over pressurizing in a vessel. Deviations from design intent are generated by applying guide wires to process parameters at different locations through the process. Example, for an inlet to a vessel, no plus flow, no flow. HAZAP is a process by which a new or existing operation, process, policy or standard is examined to evaluate what type of risks may exist within the environment. When performed properly in businesses such as refining, chemical industries, oil or gas, pharmaceutical, power generation, and other similar places, the identified hazards are sure to be remedied to prevent injuries, fatalities, and damages to the equipment. HAZAP can be a valuable tool for employers when thinking about improving workplace safety. HAZAP works by identifying all the possible unintended steps that can take place to expose the potential risks. Hazard and operability studies analysis. It has 4 phases. Define, first one. This stage requires the risk assessment team to discuss relevant ideas to ultimately focus on their efforts, define the scope, objectives, responsibilities, and select the team. Next one is prepare. This stage often includes the usage of guide words to help identify key issues within the process. Plan the study, collect all the necessary data, choose a style of documentation, arrange and schedule time and activities. Exam. The chosen guide words are applied to the examination phase as they play a role in thoroughly searching for deviations in the process. It also must be noted that all reasonable use and misuse conditions found within the process must be challenged to the point of determining if they are credible. Divide the system in question into parts and identify potential areas of deviation from intent by utilizing guide words. Point out consequences and causes of specific recognized issues. Identify if these issues are significant. Put together measures or mechanisms that protect and detect the problems. Identify mitigation measures. Document. Templates are often used for this type of documentation. Record examination and sign off on the documentation. Produce a report of the risk management measures. Follow up on the changes made and restudy those changes if needed. Produce the final report. So these are the HAZAP guide words: no or not, more, less, as well as part of, other than, early, late, before, after. Next one is FEMA, failure modes and effects analysis. FEMA is a hazard evaluation procedure in which failure modes of system components, typically process equipment, are considered to determine whether existing safeguards are adequate. Failure modes describe how components fail. The effects of each failure mode are the process responses or incident resulting from the component failure. That is hazard scenario, consequences. FEMA is used extensively in the aerospace, nuclear, and defense industries. The steps are: identify potential failures and effects, determine the severity, gauge likelihood of occurrence, failure detection. And risk priority number is given by S into O into D. Step 1. Identify potential failures and effects. The first FEMA step is to analyze functional requirements and their effects to identify all failure modes. Examples: warping, electrical short circuit, oxidation, fracture. Failure modes in one component can induce them in others. List all failure modes per function in technical terms, considering the ultimate effects of each failure mode and noting the failure effects. Examples of failure effects include overheating, noise, abnormal shutdown, user injury. Step 2. Determine the severity. Yes. Severity is the seriousness of the failure, consequences of failure effects. Usually, practice rates for failures affect severity on a scale of 1 to 10, where 1 is the lowest severity and 10 is the highest. The following table shows typical FEMA severity ratings and their means. 1 means no effect, 2 means very minor, 3 means minor, 4 to 6 moderate, 7 to 8 high, and 9 to 10 very high. Step 3. Gauss likelihood of occurrence. Examine the causes of each failure mode and how often failure occurs. Look at similar processes or products and their documented failure modes. All potential failures causes should be identified and documented in technical terms. Failure causes are often indicative of weakness in the design. Examples of causes include incorrect algorithm, insufficient or excess voltage, operating environment too hot, cold, humid, etc. Failure modes are assigned an occurrence ranking again from 1 to 10 as shown in the following table. 1 means no documented failure, 2 to 3 means low, 4 to 6 means moderate, 7 to 8 means high, 9 to 10 very high. Step 4 is failure detection. D. After remedial actions are determined, they should be tested for efficacy and efficiency. Also, the design should be verified and inspections procedures specified. Engineers inspect current system controls that prevent failure mode occurrence or detect failures before they impact the user or customer. Identify techniques used with similar products or systems to detect failures. These steps enable engineers to determine the likelihood of identifying or detecting the failures. Then, each combination from steps 1 to 2 is assigned a detection value D, which indicates how likely it is that failures will be detected and ranks the ability of identified actions to remedy or remove defects or detect failures. The higher the value of D, the more likely the failure will not be detected. 1 means fault is certain to be caught by testing. 2 means fault almost certain to be caught by testing. 3 high probability that tests will catch fault. 4 to 6 moderate probability that tests will catch fault. 7 to 8 low probability that tests will catch fault. 9 to 10 means fault will be passed undetected. RPM should be calculated for the entire design and or process and documented in the FEMA. Results should reveal the most problematic areas and the highest RPM should get highest priority for corrective measures. These measures can include a variety of actions: new inspections, tests or procedures, design changes, different components, added redundancy, modified limits, etc. Goals of corrective measures include in order of desirability: eliminate failure modes, minimize the severity of failure modes, reduce the occurrence of failure modes, improve detection of failure modes. When corrective measures are implemented, RPM is calculated again and the results are documented in the FEMA. So this is an example of the documentation of RPM. So the RPM gradually decreased from 480 to 30. Next one is fault tree analysis. Fault tree analysis is a graphical tool to explore the causes of system level failures. It uses Boolean logic to combine a series of lower level events, and it is basically a top-down approach to identify the component level failures that causes the system level failure to occur. Fault tree analysis consists of two elements, events and logic gates, which connect the events to identify the cause of the top undesired event. Fault tree analysis is a top-down approach that was originally developed in Bell Laboratories by Watson and Mions for the Air Force in the year 1962. This concept later adopted by Boeing, and today it is widely used in aerospace, automobile, chemical, nuclear and software industries. Especially reliability and safety related events are given top priority. We define the primary failure to be analyzed. In other words, identify the undesirable top event, identify first level contributors which are just below the top level using the available technical information, link these contributors to top level event by using the logical gates and OR gates, and also see the relationship so that it will help to identify the appropriate logical gate. Identify the second level contributors and link to top by using the logical gates. Identify minimal cut set. Repeat the same steps until the basic causes. Finally, complete and evaluate the FTA. Calculate the probability of lowest level elements occurrence and also measure the probabilities from bottom up top. So the symbols are circle symbol represents primary or basic failure event. The rectangle symbol represents state of the system, and the third one represents secondary failure or underdeveloped event, and the fourth symbol represents conditional event. Fifth symbol house event representing either occurrence or non-occurrence of an event, and the sixth symbol represent transfer in and transfer out symbols used to replicate a branch or subtree of the FTA. First symbol, the output event occurs when all input events occur. Second symbol, the output event occurs when at least one of the input events occur. The third symbol represents the output event occurs when all the input events occur in the order from left to right. The fourth symbol represents the output event occurs if either of the two input events occur but not both. Fifth symbol indicate the output event occurs when the input event occurs and the attached condition is satisfied. So this is the example of a fault tree analysis. This is another example. One of the important factors in qualitative analysis of a fault tree to identify minimal cut set. For instance, complex and large fault trees have to use superior tools to get the minimal cut set. A set of basic events that together cause the top undesirable event. Minimal cut set, a cut set with minimal number of events that can still cause the top undesirable event. In other words, the top undesirable event occurs if one or minimal cut sets occur. The advantages are the fault tree visually depicts the analysis that will help a team to work on cause of event in logical way that leads to failure, highlights the critical components related to system failure, provides an efficient method to analyze the system. Unlike other analysis methods, human errors are also included in the analysis. It helps to prioritize the action items to solve the problem, provides qualitative and quantitative analysis. Disadvantages are too many gates and events to be considered for large system analysis. The basic disadvantage is that it examines only one top event. Common cause failures are not always obvious, difficult to capture time related and other delay factors. Needs experienced individuals to understand the logical gates. So with this, we come to the end of the day. Have a good day.
Vishnu Audio Visual Center, like and share and subscribe and click bell icon.